Next, Olivia is going to tell us about compiling sparse workspaces. This is not about WeWork or something. This is, the computing version. So please, Olivia, take it away.
Thank you. Hi, everyone. My name is Olivia. I'm from Stanford University, and I'm presenting on behalf of Genghan Zhang, who could not make it here today. So today, I will be talking about supporting sparse result tensors by way of sparse temporary tensors, or workspaces as we call it, through the compilation of modular and general sparse workspaces. So I've given this slide many times, but there are many sparse computations in the world that we may care about, and they show up in many real-world application domains like machine learning, scientific computing, data analytics, and more. And to address these applications, a lot of research has focused on compiling sparse tensor algebra codes. And a large part of this work has studied how to iterate over sparse tensors. So for example, here I show an inner product, sparse matrix multiplication, and it's inner product because the contraction dimension is at the innermost loop. And much of this work has focused on the compilation of what we call sparse iteration theory. So it's a lowering algorithm on how you can support an expression or the right-hand side. But this is limited by the actual fixed algorithm. And so what I mean by that is when I say inner product, it's the loop nest that we show. Because a small change in the code, like the one I show here, now I'm showing a row-wise sparse matrix multiplication where I just interchanged one loop. And then a simple loop interchange requires new research ideas. So in order to support this, we needed to introduce a framework for loop reordering and also needed to introduce dense workspaces. And moreover, there's been work, so the bolded tensors are compressed and they're sparse, and there's been research focused on how to represent these compressed data structures for inputs only. Notice that A is not bolded. But again, with another small tweak, one loop interchange, we're now at the outer product sparse matrix multiplication algorithm. And this body of work doesn't know how to handle this, which I will explain later why. And then in the dense world, though, this change would be trivial for functionality. So maybe not for performance, but at least for functionality and for code generation. And then further, if we wanted to generate a sparse result tensor, again, now A is bolded, prior compilation methods also cannot do this. And they can do this in a trivial way, which is you compute the dense result and then recompress it, but they can't do it on the fly. And the reason why is because of what we call sparse scattering. So here I will show a sparse matrix multiplication example for outer product on specific tensor values. And all the boxes in white are supposed to be 0, and all the boxes in gray have non-zero elements. And one important feature to note for some background is that by a compressed result tensor or a sparse output tensor, this means that the data structure does not have random insert capabilities. And I'll show why. So let's consider the first iteration of our outer product, sparse matrix multiplication. We're iterating through the K loop or the outermost loop. So we're going to get these two input vectors from B and C. And then we're going to take these elements from B and C because they're the only elements in our vector. And I show the partial result or the partial sum matrix slice above. And then this partial result will actually be inserted into our compressed result tensor as shown. And we call this element insertion because you can, in fact, insert this element into your compressed data structure since it's currently in order. So there's no problems. So on our next iteration, at the k=1 loop, we're going to take the next vector slices on our input, and we're going to go through the first element. And the first element will produce a result, but notice through our slices that there is now a collision. So 0.6 and 0.3 need to be added together, and we're going to call this element deduplication. And likewise, when we go to the next element in our k=1 iteration, we're again going to produce an element. And this is still OK, because we're still appending to the compressed result tensor. However, a problem occurs when we go to our last iteration for this specific example. The 0.2 and the 0.1 and 1.0 are multiplied on our inputs, but it produces an element that actually comes before in order the elements that we previously computed. And so what has to happen is we have to shift our compressed tensors over, insert the element here, and then change a bunch of the data structure. And actually, we can't do this efficiently, and oftentimes compilers don't know how to generate code for this. So one solution to handle this case, this out-of-order insertion, is through temporary tensors or workspaces. And in this case, you can insert a temporary tensor that has all of the elements as coordinate points that are then sorted, and then you can build your compressed result from there. And more generally here, I show the symbolic loop nest equation for this outer product sparse matrix multiplication to show that a workspace needs to be inserted. So our workspace is this Wij, and then we also still need to generate the iteration for this workspace code. And conceptually, Wij should be able to be any data structure possible, whether it be dense or sparse, so compressed. But in practice, that's not the case. Prior work has only shown theory for dense workspaces, and they've shown theory for higher order dense workspaces, but they only have implementations for one-dimensional workspaces. And the problem with that is that our dense workspace has the asymptotic memory of the shape of the dense tensor. And so what this means is that when we run performance benchmarks or memory footprints of this sparse matrix multiplication outer product, we often get an out-of-memory error for certain data types, or for certain input data, excuse me. In the case of a sparse workspace, we can store it as a compressed tensor, and then this has the memory footprint of proportional to the number of non-zeros, and then actually this allows us to run more, enables us to run on more input data. And likewise, it's important for a compiler to handle both types of data structures because actually, in some cases with the data, a dense workspace might be better, and in other cases, a sparse workspace might be better. And again, many prior sparse workspace algorithms do exist in the literature, but these are for fixed function, and they're often handwritten. And so the issue with that is that they're not general. So no algorithm is able to actually be used for a compiler approach. And so since generality is the challenge, because we need to be able to, in our compilers, support a wide array of algorithms, and like I mentioned, support a wide array of data structures, both on the input tensor and in our workspace tensor. So to solve this, we actually introduce a compilation system. And the new features of our compiler are shown here in orange, and today I will only talk about two parts. I'll give a brief overview on our insert, sort, merge algorithm template and our insert, sort, merge function calls. For information on the rest of the new compiler features, please take a look at our full paper. So what exactly is the insert, sort, merge algorithm template? Our ISM algorithm is an algorithmic backbone. So what I mean by that is that it actually has we define an API with compress replacing the workspace iteration, and an insert, sort, and merge call replacing our building of our workspace. And this is done via this function API that then users define at runtime. So what do we mean by WAC and WAll? So these are workspace memory pools called the accumulation array and the all array. We insert elements via the insert function into our accumulation array until it is full. And then we sort elements from the accumulation array into the all array. And then we merge them together. And then finally, at the end of everything, we take our all array and then we compress it to our result tensor. So as an example, taking our running example, I'm going to show you how the algorithm works. At our first k equals 0 iteration, we're going to go through the insert phase. So the insert phase, again, taking these two input vectors, will produce this coordinate point shown in our accumulation array. Then on the next iteration, we're again going to insert our elements into our accumulation array. But now the accumulation array is full because it has a size of 2. So we're going to go into our sort phase and our merge phase. Upon sorting, in this example, there's no sorting because the points were already sorted. So we skip that and we merge it into our all array. And then we keep moving forward. So now we're going to insert the elements again into our accumulation array. insert the final element into the accumulation array. In this case, they're unsorted, so we're going to enter, it's still full, we're going to enter the sort phase. And then once it's sorted, we're going to actually be done with our computation and merge it into our final all array. At the end of the computation, we're going to take the all array, which is done, and then we're going to compress it into our final result. And this is because even though our workspace is sparse, the data structure is still not necessarily the same compressed data structure that the user may want. And even though our insert, sort, merge algorithm is an algorithm template, well, we need to actually figure out what exactly should be in those function calls. I mentioned previously that they're user-defined, but what algorithm is exactly important, what's performant, what's better for memory footprint, and so this is something that we explore. In our work, we provide two different concrete policy implementations, and we define a policy as actually what the user defines in their insert, sort, merge, compress functions at runtime. And so the first policy that we introduce, you don't have to understand this diagram, is the coordinate sort policy. So from a high level, the coordinate sort policy takes these input elements, again as coordinate points, and just sorts like a canonical coordinate list. The next policy that we implement is a bucket sort policy, and this bucket sort policy takes some function given our coordinates and then produces some value key, and then that key is used to then bucket the elements. And so this allows you to bucket elements and then sort faster. And in this case, I show the key where the key is actually just the first coordinate in your matrix. And the interesting part about our ISM algorithm template is that we're able to express the existing algorithms I showed as a categorization and breakdown of our interfaces. So here I show Gustafson's algorithm for one-dimensional dense workspaces. The insort policy for Gustafson's algorithm is a one-dimensional coordinate list and a flag list along the J dimension. And deduplication happens actually when you try and insert your coordinates when a flag bit is set to true. The sort is the same as the bucket sort that I previously described, and then the merge algorithm is Boolean indexing based on your flag, and that's how you merge. And then likewise, we're able to categorize existing algorithms into our insert, sort, merge API as well. And the key insight here is that sparse workspace algorithms actually fit into this pattern because this is the pattern needed to actually build your sparse workspace as shown in the example. So this interface is, in fact, enough. And the sparse workspace, for evaluation of our compiler, we show memory savings of, on average, 3.6 times the amount of memory for matrices that do not out-of-memory error on a 256 gigabyte machine. So here I show, again, our expression for the outer product, sparse matrix multiplication, and show the memory savings when the dense workspace does, in fact, run. But our sparse workspace approach actually enables a larger range of input data as well. And I don't have graphs for this, but I also want to say that the compiler benefits from supporting both sparse and dense workspaces because the sparse workspace on runtime can be up to 27 times faster than the dense workspace in prior work. But on the other hand, dense workspaces can also be up to 7 times faster. So the compiler should support both. And then likewise, we do an evaluation on our concrete policies and show that they do, in fact, matter for runtime. So here I show an evaluation for sparse MTTKRP with the expression shown down below, and we test 3 of the policies in our paper. So the first policy is bucket, which is a bucket sort policy. The second concrete policy we have is still that same bucket sort policy, but with a hash function instead of the original key with the outer index function that I described previously. And then the last concrete policy we have is the coordinate sort that I explained previously. And what we do is we sweep the J dimension of our sparse MTTKRP, and we show that, in fact, in some cases, the coordinate concrete policy is better, in some cases, the hash function is better, and in some cases, the naive bucket sort is better. And so the key insight is that no policy dominates, so you really want a compiler that is able to handle all of these policies and all of these algorithms through user-defined runtime function calls. In conclusion, our work enables sparse temporary tensors or workspaces as a first-class concept for tensor algebra compilation. Our work generates modular and general sparse workspaces through code composition at runtime and compilation, respectively. We provide several concrete sparse workspace policies and provide a categorization for prior work sparse workspace algorithms. And we have future work on supporting parallel sparse workspace code. Thank you so much.
All right, friends, if you have questions, please come up here to the center.
Hello. Thanks for the nice presentation. I have actually two questions. The first one is very quick.
Yes.
So in Taco, then, the workspaces are mostly dense. Am I right?
In Taco, there's a difference between the theory and the implementation. Like I said, the theory is on higher order dense tensor workspaces, so the paper is published on that. The implementation, in fact, can only support one-dimensional sparse workspaces.
Sparse workers.
Or no, sorry, one-dimensional vector dense workspaces.
Okay.
Sorry.
The second question, is the implementation available for this work or not?
We do not have an artifact evaluation, but you can send me an email and I will, yeah. We can.
Thank you very much.
Hi, thank you for the presentation, very nice. I have a clarification question. The experiments were in what context? GPU, multi-cores,
So
distributed?
they were all sequential code on CPU.
Sequential
Yeah.
code, okay, thank you. And you show like, 3 different policies about how to introduce this optimization. How do you choose between them? Is the user or is a sort of auto-tuning or it's a dynamic policy by which you select one or the other?
Yeah, that's a great question. So we make it user-defined, and we just take, like, our compiler just takes the user-provided code. So the user would have to implement all of these policies and then run all of their code, and then they would get the result. And then we envision an auto-tuning framework to sit on top of this compiler. Thank you.
Hi, great talk.
Thank you.
So with some of the examples that you showed and walked us through, it looked like it was using like a CSF or a CSR style of compression. Does this format support, or would you consider generalizing it to support other compression formats?
Yeah, that's a great question. So we are able to recompress using the theory from the 2018 formats paper. At UPSLA, I think. So based on that 2018 paper, we're able to generate code from COO to any other compressed level format. Again, there's a difference in theory and implementation. In theory, they create a wide range of level formats for more complex compressed data structures. But in actuality, in the implementation, they only show it for dense, sparse, and singleton levels. And so we are only able to generate code for the same types of levels. But the theory should exist for the other data structures.
Got it, thank you.
All right, let's thank Olivia again. Fantastic talk.